Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and today we're introducing an aspect of the next generation of networks that is often overlooked. When people talk about the sixth generation of wireless networks, or the internet, we call it 6G. The headline is usually revolutionary speed. But now, there are quieter innovations right alongside that. Security, timing, and even a physical shift in how we start to connect around the world. That shift is where the quantum internet starts to come into play. Before we go any further, let's quickly define a few things. Quantum computing is a new type of computing that uses the laws of quantum physics to process information. Instead of using bits that represent ones or zeros, quantum computers use qubits, which can be partially a 1 and partially a 0 at the very same time. That allows certain problems, like computations with very large numbers or complex simulations, to be done far more efficiently than with classical computers. The quantum internet is another important topic. And, unlike you might think, it's not just a faster version of today's internet. It's a network that connects quantum devices together. Instead of just sending classical bits, it distributes qubits and their values, again, a mix of a 1 and a 0, between locations. That enables new capabilities, like ultra-secure communication and quantum connections over long distances. The key resource that makes all of this possible is something called entanglement. Entanglement is a special quantum connection between two particles. When these two particles are entangled, their properties become linked in a way that classical physics can't explain. If you measure one, the outcome of the other is immediately correlated, even if they're very far apart. The results are random. You can't tell what the measurement is going to be before you measure it, but they are perfectly related with 100% accuracy. You might think this would allow you to send messages instantly, and it doesn't. But it does create a shared quantum relationship that could be used for powerful tasks like secure communication or even teleporting quantum states. Now we can get back to 6G internet. Our current problem is that sending quantum information with the traditional method, through fiber optic cables, is brutally inefficient because loss of information grows exponentially over distance. After enough miles, the signal simply fades away, and unlike classical signals, you can't just amplify quantum information without destroying it. So, if you want a quantum network across real cities, you need quantum repeaters, nodes placed between two locations that don't require a single fragile particle to survive the entire journey. By building these connections step by step and linking them together, quantum information can effectively span much longer distances. This sounds clean on paper, but in reality it gets messy. And that mess is exactly where Francisco Ferreira de Silva's work comes in. Francisco is one of the researchers behind a study that asks a simple question. What do quantum repeaters actually need to work on a real network? In his work, he and his colleagues modeled a connection between the Dutch cities of Delft and Eindhoven, about 141 miles apart. But instead of assuming perfect symmetry, they restricted themselves to the actual fiber grid in the Netherlands. That means real limitations on how and where equipment can be placed. That decision immediately makes the whole process more complicated. The repeater is not perfectly centered. Timings become uneven. Particles have to last longer in some places than others. To study this realistically, Francisco and his team built detailed simulations using NetSquid, a simulation platform for quantum networks. This allowed them to include real-world effects, like timing delays and memory decay, and then determine the smallest hardware improvements needed to support advanced applications. One of those applications is verifiable blind quantum computation. In simple terms, it allows a client with limited quantum capability to delegate a computation to a powerful remote computer. It keeps that computation private, and it still verifies that the result is correct. For that to work across a network, The system must meet measurable targets for quantity and speed, not theoretical perfection, but quantified thresholds. Today, I'm talking with Dr. Ferreira da Silva about what happens when you stop making idealized assumptions and start modeling quantum networking in the way it would exist in the real world. Let's get into it. Firstly, can you explain to us what your goal is in furthering quantum internet? What is the potential benefits of the technology?
Yeah, certainly. So I like to think of it along two axes. One is secure communication. Quantum internet consists of quantum devices connected in a quantum way, which is an informal way of saying quantum systems sharing entanglement between one another. It's well known for a few decades already that the properties of entanglement can enable more secure communication that is possible with classical means, with quantum key distribution being the best known instantiation of this phenomenon. And another angle is more broadly interconnecting quantum systems. So quantum information processing and communication just has different properties than what is possible classically. You might have heard of quantum computers that for certain classes of problems can solve them much more efficiently than what is classically possible. And for example, by connecting quantum computers at a distance, you can distribute these computations, you can enable secure remote access to people who want to make use of these computers that they might not themselves have access to. And another angle is that the properties of entanglement enable stronger correlation than what is possible without entanglement with applications to distributed decision making.
And quantum repeaters are always obviously the primary element of your research, particularly. What problem do they solve within the creation of this quantum internet?
Yeah, so quantum repeater is a proposed device to enable the generation of entanglement at long distances. So maybe I can start by explaining the challenge and making the analogy with the regular internet, and then explain why you might need a quantum repeater. So for if you want to connect to non-quantum devices, which people in the field often refer to as classical, coming from classical mechanics versus quantum mechanics. Something you might do is just you have an optical fiber, so like a tube connecting two locations, and you send light photons along this fiber. And the information you want to transmit is encoded in these particles of light. And so this way you can establish communication between 2 points. The transmission of photons along a fiber is a lossy process. So photons get lost along the way. And the way you solve this classically is relatively simple. You do amplification at regular intervals. Which basically just means you receive your signal at some point and you copy it and you send it again many times. And as long as some photons make their way, you're fine. This is kind of a simplified picture, but it's the general idea. One property of quantum mechanics that is useful for security purposes, but also makes quantum communication more challenging is the no cloning theorem, which means that you cannot arbitrarily copy quantum states. So this simple approach of just copying photons and sending many of them again doesn't work a priori. And so this idea of just straight up having a repeater that would copy your quantum photons and pass them along does not work. But you can still have an analogous of this, which is what people mean when they say quantum repeaters, in which the idea is basically, say, if you have a long distance that you want to cover, so, I don't know, 500 kilometers of fiber, if you just try to send your quantum signals as photons along that link, the probability that one makes it all the way to the end is extremely low. You're never going to get there. What you can do, though, is split the path into many smaller links and generate your entanglement along all these smaller links and kind of glue them together, which is a process that is known as an entanglement swap. And the devices that you use for this smaller entanglement generation and gluing are what is known as quantum repeaters.
So I imagine these repeaters don't only come with benefits. They don't only allow us to transmit more information. What problems arise when we add repeaters into the system?
Yeah, so maybe now it's good to draw a distinction between kind of the idealized picture and how they actually work in reality. In the idealized picture, they basically come with advantages only, like they enable a higher rate of entanglement generation in comparison with the picture without repeaters. In reality, they are themselves very lossy and noisy devices, and it's actually just very hard to realize them. Like the first proposals to, like the first theory proposals of how you could do this, they date back already to the late 90s. So it's been almost 30 years now. So I suppose the basic idea is not that complex, but realizing them in practice is actually very, very challenging. So they basically introduce a bunch of extra operations that you need to do on your quantum systems to get the effect that you wanted to. And quantum systems are just fragile, complex things. So every time you do one of these operations, you lose some photons along the way, you introduce some noise. And there's basically a threshold of quality you can think below which, if your repeater is not good enough, then it's actually hurting you more than it helps you. The device needs to go to a certain level of quality before it even starts helping you. And I would say just very recently, in the last couple of years, are we starting to be able to manipulate quantum systems into repeaters at a level where they do help you. But if I had to guess, it's still going to be a while until you see quantum repeaters deployed in the wild.
So you decided to focus your quantum internet studies on a specific application, verifiable blind quantum computation. That's a lot of words. What does that phrase mean in simple terms?
Yeah, so that connects to one of the applications that I mentioned earlier when you asked what a quantum internet is good for. And I said something along the lines of securely delegating computations to a quantum computer if you don't happen to have access to one. So let's imagine a future in which we've built quantum computers. We've found them to be useful for a certain set of tasks. You can probably imagine that, at least for the foreseeable future, there's going to be very few entities that are capable of building and maintaining these computers. I would think big tech corporations, maybe governments of powerful, wealthy countries. You can also imagine that many people will want to have access to them. And let's say you're a small startup and you have some great idea for a quantum algorithm that you want to run and get results of, but you don't happen to have a big enough quantum computer yourself. Google does have one, but if you reveal your idea to Google, then maybe you're just out of luck. They're just going to take it. Blind quantum computing, or verifiable blind quantum computing, gives a solution to this problem. So quantum computing, I'm going to assume those two words are fine. Blind in this context means that if I have a computation that I want to delegate to Google's quantum computer, Google learns nothing about the computation I'm performing. Verifiable means that I have guarantees that Google's quantum computer is actually implementing what it claims to be implementing. And it turns out that this is possible under certain conditions, as long as myself or my quantum device and Google's quantum device share enough entanglement to enable this. And some of the work I did in my PhD was to kind of map out, okay, if I want to run exactly this instance of verifiable blind quantum computing on exactly this link between these two locations, what does that mean for the quantum repeaters I use to implement the quantum channel between the two locations? Like, how good do they need to be to enable this?
And so why did you choose that specifically as a benchmark for creating a strong quantum internet?
Yeah, that's a good question. So actually, the majority of research into quantum communication and the quantum internet uses quantum key distribution. This other application I also mentioned as a benchmark. We wanted to do something different for a couple of reasons. One is that quantum key distribution, QKD, has been more extensively studied. Two is that it's not inherently an entanglement requiring application. You can actually use simpler devices to do quantum key distribution, which is actually also the reason why it's the only quantum communication application that's already commercially available and has been for some time already. And so blind quantum computing is kind of perhaps the best known instantiation of a truly quantum internet application that is out there. And in combination with that, there was not, to the best of my knowledge at the time, any in-depth study on how you translate from a specific instance of VBQC, verifiable blind quantum computing, into requirements on the hardware you use to implement the link.
Thank you. What I found most interesting was how your modeling was so accurate to real-world limitations. What specific information were you able to obtain in comparison to someone who may not have had as realistic of models?
That's kind of you to say. I guess realistic is a spectrum, so maybe I'd hesitate a bit to call our modeling realistic. It's definitely closer to reality than most of the modeling you see in the literature, to the extent that it took into account a couple of things that people usually don't consider, namely that assuming you want to make use of existing optical fiber, which you probably do because laying new optical fiber is a bunch of work and costs a bunch of money, then you're going to have to live with whatever's there, including the fact that it's not laid as the crow flies typically between the two locations that you want to connect. Nodes along the way are also not placed symmetrically, which turns out to be bad for entanglement generation, and it typically has more loss and more loss than what people assume in idealized models. And so what we did that is not so common in the literature is to, instead of make some idealized assumptions about the fiber links you have access to, we actually drew on data from deployed optical fibers in the Netherlands and took that into account in our modeling. And to be honest, the qualitative result is not surprising at all. It's just like it becomes harder if you have to account for all these limitations than if you make some idealized assumptions. The purported benefit of doing this is like, hey, we can quantify exactly how much harder it gets. Whether that's useful and realistic depends on how likely you are to do the actual deployment that we studied. And I would guess the answer is you're not very likely to actually do that, but it makes a point.
So kind of the final topic. If quantum internet is to become the future, what are the biggest bottlenecks that we need to overcome?
That's a good question. So first, maybe I'd start by qualifying the sentence, it is to become the future. I don't imagine a future in which the quantum internet supersedes the existing internet. It's more like an extra technology that will exist alongside it. So I think for many, many tasks that you want to perform, the classical internet is perfectly good. And it's generally a much simpler technology that already works and is deployed worldwide. It's more like there's a specialized set of tasks for which you might want to use the quantum internet. And I'd actually argue that the bottleneck at the moment is clearly identifying what these tasks are and identifying what are the use cases for this technology. So I think at the moment there's a big divide between what the academic community does in terms of coming up with potential uses for the quantum internet, in which it's all very abstract and algorithm based, and there's not that much work bridging, say, the this academic literature with what practitioners in, say, classical networking or just other fields that might benefit from the technology, what they might want of it. And I think if this is to become an actual deployed technology that benefits society at large, like has to be a lot more dialogue and a lot of hard work in identifying use cases.
And so do you think we're close to overcoming these issues? What type of time scale is the quantum internet going to become something really viable in real life?
Yeah, I think that's a good question, and making predictions is hard, especially about the future. Um, I think it depends on what you mean by quantum internet. I think like the earliest instantiations of it, which would be just point-to-point entangled links between quantum memories up to distances of, say, 50 kilometers or so. Actually, stuff that does not require repeaters. I would say that's fairly close. I would expect before the end of the decade to see the first examples of that. If we're talking worldwide entanglement over 1,000+ kilometers and topologies that are more complex than just point to point, then I would guess we're still over a decade away.
Cool. That's all the questions I have for you. Thank you so much.
Yeah, no worries. Thanks for having me. This was fun.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.